Today we're looking at 3D trigonometry. Now this is really not too much harder than two-dimensional trigonometry, it's just that we might need to solve things in more than one triangle. So these basic principles will help you. I suggest writing these down in your book. What we basically want to do is, where possible, we want to draw two-dimensional triangles. And you can do that by imagining that you're looking at your three-dimensional picture from above or from the side. So they often call this a plan view, as though you're looking straight down at it. You want to identify which triangle has got enough information in it that you can actually solve it for a missing angle or a missing side. Now, remember that if we're saying the sine of some angle is equal to something over something, we've got basically three unknowns here. Now, this could be sine, cos, or tan that we're dealing with, but we've always got an angle and we've got two different sides. And if we're looking for the angle, we'll know both of those sides. And if we're looking for one of the sides, we'll know the other side and we'll know the angle. So make sure you have two items out of three. If you do, you can solve for that unknown thing. If you've only got one item in the triangle, then you need to look for another triangle to work with first. So solve for the unknowns. That's a bit messy, sorry. The unknowns in one triangle to help you solve for an unknown in another triangle. So this means you sort of need to look at what the end solution will be and work backwards to find where to start. Now, if you can't solve for a side or an angle in any of the triangles, and this will be a really challenging question, you can make an algebraic expression for it. And perhaps if you can make two different algebraic expressions, you can equate them. So perhaps you're finding, say, the height of some tower and you can't work out what it is, but you can say h equals something that has algebra in it. But perhaps you can say h is also equal to something else. Well, if h is equal to this and h is equal to that, then those two things might be equal to each other, and that might give you a method for solving. My last tip is be prepared to use Pythagoras' theorem, because that's super handy. We always know that a squared plus b squared is equal to c squared, where c is the hypotenuse, or the long side of the triangle, the one that's opposite the right angle. So be prepared to throw your expressions into that, and that should give you a way out when you've got a really tricky problem to solve. Now in this example, we've got a rectangular-based pyramid. Now, when it comes to drawing these things in 3 dimensions, a little tip. Drawing something like this, if you draw, say, a parallelogram that just looks like it's a rectangle pushed on its side, and then pick what you think is the actual center point of the base, and you can do that by just drawing in the diagonals. Go straight up from there and put a dot, and then just join up all of the corners to that dot. Okay, it's a little bit dodgy, but you're getting the idea. So 3D drawing doesn't have to be crazily difficult with a few simple tips. But what I like to do then is perhaps use some colour to highlight where the individual two-dimensional triangles are. So in this example here, I could make a triangle in purple that goes over to the midpoint of this side, and a line here that goes down the centre of one of those slanty triangles. And now I've got a right angle triangle here, which I could make purple so that I can see what's going on in that purple triangle. And I can imagine looking at that, standing over here from the side and looking at it side on. Now, if I just draw that purple triangle, it's 10 meters tall, and if my base here is 8 meters wide, then it's clearly going to be half of that, so it's going to be 4. And now if I want to, I could use Pythagoras to find the length of this, and I could also find any of the angles that I like, because I've got a right angle here. If I look at the base, which is just a rectangle, looking straight down, let's draw that one in black, then it's going to look like this, looking straight down, and it's 8 meters. Well, that's probably not very well to scale, is it? Because it needs to be bigger one way than the other. It's going to be 9 meters this way and 8 meters this way. So clearly I could draw in diagonals if I want to, and now I have right angle triangles there as well. And I could use Pythagoras to find the length of this, but I can also find these angles here using my trig. I could also make triangles that go, perhaps if I draw in this diagonal here in red, then I could make a right angle triangle here that includes the center again, but goes off at a slanty edge there. So in this question, we're going to find two different angles here. We're going to find this one, which I'll put in red, let's call this alpha, and it is the angle between the base and the slanty edge going up. But we're also going to find in this purple triangle, this angle here, which I'll call beta, which is the angle from the center of a side to the apex of the pyramid. So what information have I got and what am I going to need? Well, let's look at finding alpha first. If I draw just that red triangle, then looking at it from the side by standing over here, it's going to be 10 meters tall. The length along the base, I don't know yet, but I do know that it's half a diagonal, so it's going to be whatever that length there is in red. And I'm trying to find alpha, so I'll label that. Now, I don't have enough information there to solve anything in that red triangle, but if I knew this side or this side, I would. Now, which side is easiest to get? I'd say this one here. If I knew what this side is, I could say tan of alpha is 10 on that, and I'd be able to find alpha. So, recognizing that this red line is also on this triangle I've drawn over here on the side, I could actually make a right angle triangle here. Let's make this one in blue. Now, if I just look at this triangle, which is quite small here, and draw it by itself, then I know that if this is 9, then this is 4.5 here. And if I know that this is 8, then this is going to be half of 8, so it's going to be 4. And I can quite easily use Pythagoras' theorem to find this side. Let's call it C. So I can say 4 squared plus 4.5 squared is equal to C squared. So C squared must be equal to whatever this is, and C is going to be the square root of that. Now, 4 squared is 16. Calculator here, so we can get this done. So I've got 16 plus 4.5 squared, that gives me 36.25. And the square root of that is, let's say, 6.02 to 2 decimal places. Now, there's straight away a chance here of rounding this off and then carrying my error forward into the next calculation. I don't want to do that, so I've got 2 choices. I could either call C the square root of 36.25, and I could use that in my next calculation, because that's exact, isn't it? Or I could save this, I could store this in my calculator as, let's say, A. Now, how do you do that? Well, you go Shift, Store, and then you press one of the red buttons there. I'm going to call it A. So next time I want that number in exact form, I can press alpha A, and it'll come up. It's probably a little bit quicker than typing in square root of 36.25 again. And I don't want to just use 6.02 because that's not exact, that's rounded off. So now I know what C is, that's this here, that's exactly what this is here, right? So I could call it little c, and I could say, all right, I've got that now. I'm also calling it big A, a little bit confusing, but I think you see where we're going. So now in this triangle, I've got my opposite side and I've got my adjacent side. So I need to say that the tan of alpha is 10 over, and I could put it in here as 36.25. So if I want to find alpha, here I found the inverse tan of this side, so I need to take the inverse tan of this side as well. And if I put it in like this, either with the square root of 36.25 or as alpha A on the bottom, I'll get it in exact form. And we get 58 degrees and 57 minutes to the nearest minute. Now, if I was going to use this calculation in the next part of my work, I would save this as well, maybe save it as B in my calculator so I can use it again. I'm not sure whether I'll need to use it again because over here I'm finding beta. Let's have a look. Well, let's save it just in case we need it. I'll Shift Store B and I'll call this B. Okay, so our next piece of working to find beta, well, beta is quite straightforward because we actually have, do we have it? Yes, we actually have everything that we need to find beta straight off, and for this section we don't actually even need to use Pythagoras' theorem. So we can say that we have the opposite and the adjacent sides, so the tan of beta is going to equal 10 over 4. So beta will be the inverse tan of that. You can simplify that fraction if you want, or just put it in exactly as it is, saves you making a mistake. And we have the inverse tan of 10 over 4, which means that beta is 68 degrees and 12 minutes to the nearest minute. Now, when we've finished, we want to check, does that seem around about right? So we had 68 degrees here, whereas our previous answer was 58. Would it be right that this is a more slanty side? Yeah, that does seem right. It'll be a steeper angle to look up from here than it would to look up from there, because that's further away from the base of this tower, if you want to think of it as that, or the base of the pyramid. So different methods there. I needed to use Pythagoras' theorem for part of it. One of my calculations was 2 steps. The other one was pretty straightforward. And depending on what information you have, you'll need to just work your way around the triangle.